All right, we are back with question number 6. And again, this is the Physics 1, Term 1, Periodic 1 from last year. And so we have a question about a duck. A duck is walking with a constant velocity of 1 meter per second. He walks for 20 seconds. How far does the duck walk? For 5 points. Well, let's see. First, let's constant velocity. That means the duck is not speeding up or slowing down. He's cruising with a constant speed of 1 meter per second. So if he does that for 20 seconds, he'll end up walking 20 meters. But if you want the official equation-wise solution here, we can always do that. Check it out. Let's write down everything we know. Well, V naught, V final. If the velocity is constant, that means that V naught and V final are the same, right? Because he's not speeding up or slowing down. They're both 1 meter per second. And this may seem too easy to have to write these quantities down. It is, but nonetheless, at least it's easy if you've done a few of these, all right? Nonetheless, it's a good idea to write these things down. Okay, and V final is 1 meter per second. Okay. Well, then, and I want to know, T is 20 seconds. And I'm looking for how far does he go? That's delta X. All right. So you could do this a couple of ways. Again, you know, most of you, okay, can kind of have the sense here that if he's moving at 1 meter per second for 20 seconds, it's going to end up being 20 meters, his displacement. Still, let's see what the equations say. So delta X is V average times T. V average. Well, what's the average velocity? It is 1 meter per second, but let's just double check to make sure. Remember, V average is 1/2 of V final plus V naught, just to be sure, to show you that this is consistent. It's logically consistent. And so V average is going to be 1/2 of 1 meter per second plus 1 meter per second, because as V final and V naught, they're the same. So that's 1/2 of 2 meters per second, which amazingly is 1 meter per second. All right. So 1 meter per second times 20 seconds is 20 meters. Okay, so dimensionally, meters over seconds times seconds, the seconds cancel. So you have 20 meters. Alrighty then, let's look at another way of determining an answer to this. We could also use delta X is equal to V naught times T plus 1/2 AT squared. Okay, acceleration. Did that show up anywhere in the problem? No, it didn't. And acceleration, the definition of acceleration is it means you speed up, you slow down, or you change the direction that you're moving. Well, if your velocity is constant, you're not speeding up or slowing down. That means that your acceleration is 0, right? Or look at the definition of acceleration. So acceleration is v final minus v naught over t. In this case, the v final is a meter per second. The v initial is 1 meter per second divided by, I don't know what the time is. It really doesn't matter what's down here because 1 minus 1 is 0, usually, in this universe, okay? So your acceleration is 0. That means that this last term, if a is 0, this whole part is 0. So it's just v times t, all right? And there you go. Problem done. Yay. Let's look at the next question, okay? What happened? Okay, question 7. The same duck is walking with a constant velocity of a meter per second, walks 20 meters. What is the acceleration of the duck? We just answered that in the previous question. Since the duck is not changing its velocity, then its acceleration is 0 meters per second. Question done. All right, so here's number 8. A car with an initial velocity of 20 meters per second slows down at a uniform rate to stop in a distance of 100 meters. What is the duck's acceleration? What? This is not a trick question. This is an example of goofiness on my part. All right. Either I should change the car to a duck, or I should change the duck to a car. Okay? To be consistent. Sorry about that, folks. It happens. In any case, let's just say it's a car, all right? So we have a car with an initial velocity. I'm going to draw a little picture, first of all. So here's this car zipping along, and so it has a v naught of 20 meters per second. And then a little while later, it slows down and it stops. So that v final is 0 meters per second. And the distance, okay, that it takes from when it starts to slow down and when it stops, that's delta x, is 100 meters. And the question is, what is the car's acceleration? All right, so let's see. I've got everything here. V final, V naught, delta x. I'm looking for A. I want to find acceleration. So, there are two expressions in your list of equations that have acceleration. One of them is, maybe 3 equations. One of them is this. Acceleration is V final minus V naught over t. We also have this equation. Delta x is v naught t plus 1/2 at squared. And the third one is v final squared minus v naught squared is equal to 2a delta x. So look at what you have. Look at your givens in the problem. I know I have velocity, v naught and v final, and I have a displacement. Well, I do not have time, right? Time is not explicitly mentioned in the problem. So do I have one of these equations that doesn't require time? Yes, there is one. It's the last one I just wrote down here. This guy, it requires time. This one requires time. So yeah, you could do an intermediate step and determine time, but it's already been done for you, which is how we derived this equation. All right. And we're looking for acceleration. So now we need to solve this guy right here for acceleration. And this requires algebra. It's algebra time. Yay, algebra. All right, so we got v final squared minus v naught squared is 2ax. Let me rearrange this first of all. So I'm going to write down, because usually what you're looking for is going to be like on the left side of the equal sign. So let's just flip what's on the left side with what's on the right side. So 2a delta x, oh shoot, equals v final squared minus v naught squared. Okay then. Oh, check it out. V final here is 0. That means that it goes away. Good deal. I can just, that's 0. All right. So then now I know that what you're used to doing, many of you, is to put the numbers in right now and crank out the value of acceleration. But you're much better off in this class, okay, to solve in terms of variables. That is, using algebra, rearrange the variables, then plug in the numbers as the very last thing, okay? So then I want to solve for a. So to get a by itself, well, the first thing to do here would be to divide both sides by 2 by 1 over 2 delta x. So that means that on the left side, I end up with a. And on the right side, I have minus v naught squared divided by 2 delta x. And now you can put in the values of v naught and delta x. Let's make some room over here. Okay, so putting in the values, I have a equals minus, so v naught is 20 meters per second, and that's going to be squared, divided by 2, and the delta x is 100 meters. All right. So 20 squared is 400, right? So on the top, I end up with minus 400, and the units are also squared. So I have 400 meters squared per second squared, divided by 2 times 100 is 200 meters. All right. Then finally, so number-wise, I have minus 400 over 200 is 2. And then the dimensions are going to be meters squared over meters. One of the meters goes away. Yoink, yoink. So I'm left with meters per second squared, which is a unit of acceleration. That's a good thing. And so there we go. Now, the negative sign, remember, so with these quantities that we've been dealing with, displacement, velocity, acceleration, they have a direction. They point left, right, up, down, plus x, minus x. So the negative value here in this problem indicates the direction of the acceleration of this car, which is in the opposite direction that it's moving. Okay. If you play around with the app I showed you in a previous presentation here, you can change around initial velocities and accelerations. And in this case, yeah, if the car has a velocity in this direction and it has an acceleration in the opposite direction, that means the velocity is positive, the acceleration is negative. That means the car's slowing down, as it is in this problem. But a negative acceleration doesn't always mean the car is slowing down. For example, we could have a car that is moving to the left. It had a velocity of, let's say, minus 5 meters per second. And it's also accelerating at a rate of, A, is minus 2 meters per second squared. This car is speeding up towards the left, okay? So be careful about, what you're, thinking about what acceleration means in terms of speeding up or slowing down. If the acceleration and velocity have opposite signs, yes, that means whatever it is that's moving is slowing down. If they have the same sign, it is going to be speeding up. And we'll talk more about this at a later time. So that's good for right now, okay? And we'll finish going over this exam this week in class, okay? Have a good evening.